So let's discuss different types of operators. Let's start with arithmetic operators. There are basically two types of arithmetic operators. One are binary and other one is unary. The unary, the unary operator has higher precedence compared to the binary operators. The unary operators take only one operand and binary will take two operands, right? The example of unary operator is like this. If you want to define a -5 or +10, these are unary operators. You can define the sign of any value. And binary operators, there are different binary operators like this: multiply, division, add, subtract, modulus. Apart from this, there is one more binary operator called power. If you want to do a power b, that means a over b, then you can use this operator double asterisk, which will give the power of a over b. Okay, let's take examples for this. Let's take an example of an operator c is equals to, let's take c is equals to a into b. So if I define my a is equals to 4-bit binary 0101 and b is equals to 4-bit binary 1001. So this is a 5 and this is a 9. So my output c will be equals to 45, right? But you need to remember, if any value in one of the operand or both the operands having an x or undefined variable, then your entire output expression will be x. Why? Because if you don't know what is the value of x, it can be either 0 or 1. Based on this, the output can be either, in this case, it can be either, if it is 0, then it will be 2, and if it is 1, then it will be 6. So you don't know if what do you get if you multiply the b with 2 and if you multiply the b with 6, right? So the complete expression will convert into x. This you need to remember. Now we'll see one more important thing you need to remember while using the modulus operator. What does this modulus operator will do? The modulus operator will give you the remainder of the division between two numbers. It is similar to the C language. In C language also we have the modulus operator. So let's take my A mod B. Let's take my A is equal to 13 and my B is equals to 2. So the remainder will be 1. So the output will be 1. But you have to remember, the modulus operator will always take the sign of the left side b. What I meant is, if I have a is equal to -7 and my b is equals to 2, then my remainder will be -1. But if you have a modulus like this, 7 modulus -2, my remainder will be +1, because it will always take the sign of the left hand operand. This thing you need to remember while defining the modulus operator. Now let's see what are the different logical operators that are available. These are the three different logical operators that are available. The logical negation is a unary operator, whereas the logic AND and logic OR are binary operators. So let's take an example of the logic operators. My A is equals to 4-bit binary 101 and my B is equals to 4-bit 1010, 4-bit binary 0101. Right? If I evaluate A and B, so what does it do? It will do the logic operation between A and B. Since A is a number which is not equals to 0, so it is equivalent to 1, and B is also a number which is not equals to 0, so it is equal to 0. So 1 and 0 will be 0. So the output of logic operator will always be either 0 or 1 or x. You will get x when any of the input is having a x, right? Otherwise, the output will either 0 or 1. It is checking whether the inputs are logically true or false. Let's take one more example. If my input is A and B, then it's same inputs. If I do the logic operation of A or B, so in this case, my A will be 1 or B will be 0. So 1 or 0 will be, my output will be 1. So this is how you will get the outputs for logic operators. It will be useful to check whether the A and B are true or false. You will get 0 if let's say my C is equals to 4 tick binary 0 0 0 0. In this case, if you perform logic operation between A and C, then A will be a number which is not equal to 0, so it will be 1, and C is a number which is equals to 0, so 1 and 0 will be 0. Okay. So here I did a mistake actually. My B is 1, right, because it is a number. So 1 and 1 will be 1, not 0, right. Here also my B is a 4-bit value which is not equal to 1. So 1 and 1 or 1 will be 1. So let me draw one more time. The uses of logic operators is to check whether the inputs are logical true or false, right. The output is always either 0, 1 or X. The output of logic operators is always either 0 or 1 or X. So let's take example. A is equal to 4 tick binary 0 1 0 1, and B is equals to 4 tick binary 1 0 1 0, and C is equals to 4 tick binary 0 0 0 0. So if I do logic operation of A and B, then my output will be A will be considered as 1 because it is having a non-zero value, and B is also having a non-zero value, so it will also be considered as 1. Then my logic operation will result into an output of 1 and 1 is 1. Similarly, if I do A and C, then A is 1, and since C is a value of 0, 1 and 0 will result into output of 0. So this is the output of logic operators, and if you have any X inside the logic operators, it will go into X. If you have any operand that is X, then your output will be X. Now let's see what is relation operator. These relation operators very much similar to the C language. Like if you want to see whether the operand B is greater than A or C is greater than or equal to A, like this you can check by using different relation operators: greater than, less than, greater than, equal to, less than or equal to. Let's take an example. Let's say A is equals to 4 and B is equals to 3. Then if A less than or equal to 3, then in this statement the output will be 0 because it is false. A is not less than or equal to 3, as well as if you take A less than or equal to B, in this statement also the output is 0 because A is not less than or equal to B. The output will be either 0 or 1, and it will go to X if any of the operator is having X in the value. Next thing, let's see what is equality operators, right. In the equality operators, you have two different cases like this. If you can check directly whether A is equals to B or A not equals to B, and there are two extra things called case equality and case inequality, where if you want to check B double equals to triple equals to C, what does this do? In case of equality operator, there is a chance of output of either 0 or 1 or X. But in the case of case equality, the output can be either 0 or 1. So let's take an example. Let's take my A is equals to 4 tick binary 1 0 1 0, and my B is equals to 4 tick binary 1 x x z. In this case, if I perform normal A is equals to B, since A is not equals to B, it will give me an output of 0. But there are x's inside this, so the output will be x. But in the case of A triple equals to C, let's take my let's take B and C. Let's take my C is also B 1 x x z. Then in this case, since both B and C are same, even though there is a x and z's that are present inside the operands, but still it will give me the output of 1 because C is exactly equivalent to B. In this case, C and B are 1x z. So if they are exactly equal, then output will be 1. If there is any change in this, let's say my C is equal to 1x0z, then B triple equals to C will give me 0 output. Okay. This is the use of equality operators. Now let's see bitwise operators. What are these bitwise operators will do? It will do bitwise AND or XOR or XNOR operation between two operands. Let's take two operands A comma B, where A is equals to, let's take 4-bit binary 1010 and B is equals to 4-tick binary 0110. In this case, if you perform bitwise operation of A and B, it will do 0 and 0 will be 0, 1 and 1. It will do bitwise operation of this operand on these operands using this operator symbol AND. So 1 and 1 will be 1 and 0 and 1 will be 0. Again 1 and 0 will be 0. So this is how you get the bitwise operation. Let's take the sizes are different of A and B. Let's take my A is a 5-bit number. In this case, it will assign my B to a 5-bit number by adding a 0 to it. By this way, always the output will be equivalent to the maximum size of the input operands. If my input operand is, let's say, 7-bit and the other operand is only 5-bit, it will add 2 extra zeros to it to match the length of the other input operand. So finally, my output value will be equal length of the input operands. Okay. You can perform different bitwise operations like bitwise AND, OR, NOR, and XOR. Remember, we have seen the truth table of different operands in gate level modeling. There, you will have 4 different values 1, 0, 1, X, and Z. But in this case, you have only 3 different values 0, 1, and X. The Z is treated as X. So, if you draw the truth table of bitwise AND operation, it will be like this. 0 into 0 is 0, 0 into 1 is 0, and 0 into x is 0. Whenever there is 0, the output is always 0. Similarly, whenever there is 0, then output is always 0. In this case, 1 into 1 is 1, and 1 into x is 1, x is 1, 1, and x will be x. There is no z in case of bitwise operators in data flow modeling. Okay. This is the truth table of bitwise, and you can draw the truth table of bitwise OR, XOR, and XNOR also. There is one operand called bitwise negation. What does it do? It will take only one operand. Let's say my B is equals to negation of A. So if my A is equals to 4-tick binary 1010, then my B will be, it will invert bitwise of all these numbers. So it will give me 0101 as my output. Okay, that is the advantage of bitwise operators. Now let's see what are the reduction operators. The reduction operators will be performed on one operand, whereas the bitwise operators will be performed on two operators. So always remember the symbols of these two are very similar, not similar, the symbols of these two are exactly same, but the way you perform them, the way you use them will be different. If you have a reduction operation like this, end of A, the reduction operation will only take one operand, whereas the bitwise operation will take two operands like this, A and B. In this case, it will perform bitwise operation between A and B, but in this case, it will reduce A to a single value. So let's take an example. If my A is equals to 4-tick binary 1010, then end of A will perform bitwise and inside the A. So it will perform 1 into 0, which is 0, and then 0 into 1, which is 0, and then 0 into 0, which is 0. So it will convert the vector into a scalar. Okay. What is the use of these bitwise reduction operators? Right. We already know bitwise operators can be used to perform normal AND OR operation on any number of inputs. Right. If you want to design a AND gate between A, B, and C, you can directly write the bitwise operator of A and B and C. But what is the purpose of this reduction operator? Why do we need these reduction operators? Let's take a practical example like this. If you want to check whether the stack is full or not, right? You, if you see the computer organization, there is a stack where it has address starting from all zeros to all ones, right? If let's say it is a 7-bit stack, then there are 7 address lines. it starts from all the way from 0 to all the way from 1. So if you want to check whether the stack is full or not, what you need to check? You need to check whether the address is having all ones. In this case, one way to check is you can directly check if my address, this is my address, let's say, if my address is equals to double equals to, because we are checking logical equality, so double equals to, it's a 7-bit address, so 7-tick binary all ones. In this way, you can check if my address is equal to 7-tick, then the result is equal to yes, stack is full. Stack is full, right? This is one way to do. But if you don't know what is the number of address lines that are present in stack, let's say if you want to generalize this thing, let's say if it is a 9-bit stack, then you have to check 9-bit binary. Let's say if it is a 12-bit stack, you have to check 12-bit binary. So generalizing this statement is very difficult. So we need to have a generalized statement that can define or that can identify whether the stack is full or not. That can be easily doable by using a bit reduction operator like this. What does this reduction operator will do? It will do end of all the values. So I will assign my b is equals to end of address. So what does it do? It will perform end of all these operands. Then it will give me an output. It will give an output 1 only when all the all the bits inside my address is 1, right? So by this way, you can directly check, you can directly write 2 lines like this. My b is equals to end of address. Now this address can be any number of bits. It can be 20 bits, 40 bits, 30 bits. It doesn't matter, because it will perform reduction operation on this complete address, and then it will give you a single bit output, either 1 or 0. It will give one output if all of the bits inside the address are ones. Once you get this, you can directly check if my b is equals to 1 or not. If my b is equals to 1, you can say yes, stack is full. If my b is equals to 0, then you can say stack is still having some space, right? Similarly, you can use bitwise OR operator to check whether the stack is having space or not, like this. I mean, if you want to check whether is there any single bit inside the address is 1 or not, by using a OR operator, right? OR operator will give, if you perform, let's take an example, let's say c is equals to, what is the operator for reduction? Or this or address. So what does it do? It will give me output 0 only when all are zeros. In the other case, if there is any single one inside this, it will give me an output of c is equals to 1. So you can check whether the stack is at the initial position or not by using this OR address. If my output is 0, then you can tell yes, my stack is at the initial position. So that is the practical example of these reduction operators. Now let's see the shift operator. This is very much similar to your C language also. You have right shift and left shift. If you perform right shift, the A will be right shifted twice, or you can define how many bit you want right shift by using whether you want to define 2-bit right shift or 4-bit right shift by doing like this. So where these right shift or left shift will be useful, it will be useful for designing a multipliers by using a shift and add algorithms. There is 2 other right shift and left shift algorithms like this, which will be an arithmetic right shift, which is very similar to your C language. It will give the cyclic right shift, arithmetic right shift, or arithmetic left shift. Now let's see what is the concatenation operator. The concatenation operator is used in order to get the string concatenation or data type concatenation. In this case, if you have, let's say, 2 inputs, A is equal to 1-tick binary 1 and B is equals to 2-tick binary 0 1. If you want to concatenate A and B and put it into Y, then you can directly write concatenation of A comma B. So the output will be 1 0 1. Y is a 3-bit value of 1 from A and 0 1 from B. Either you can use variables or you can directly write Y is equals to A comma B comma let's say I want to add 4 bits extra to this 1010, then my y output will be 1 because of A and 01 because of B, and then these extra 4 bits like this. Okay, you can use part of the vectors also. Let's say I want to add the B0 only. You can define like this: y is equals to A comma B0 comma 2 bit binary 01. In this case, the output will be 1 because of A, and 0th value of B is 0, and then 2 bits of 01. This is how you can concatenate the values in Verilog. And there is one more operator called replication, where you want to replicate the data defined by number of times you want. So let's take an example. If you want to replicate the B operand 4 times, so how to do that? You can directly write 4 of B. So what does it do? My output y is equals to 4 times the B operand will be replicated, 0 1 0 1 0 1. You can even add two different operators and replicate like this: y is equals to, let's say, 4 of A comma 2 of B. So it will do 4 times A. My y is equals to 4A and 2 B's, 0 1 0 1. So this is the purpose of this replication operator. It will be very useful when you want to concatenate two different datas. Now let's see what is a conditional operator. We have already seen this conditional operator many times. It will be useful to design a 2:1 multiplexer or if-else statement. So if you have question mark and column, what does it do? It will check whether this expression is true or false. You can put any uh, wire or net here, or you can put a expression also here, A plus B. It will check for this expression whether the expression is true or false. If the expression is true, then execute this true line of statements. You can put either value or you can put an expression here itself. And then if the expression is false, then it will execute the expression or value that is presented in this. So this is my y output. Let's say if my A is equals to 0, then it will execute y is equals to b, and if my A is equals to 1, then it will execute y is equals to c. We'll see how to design a 4:1 multiplexer using by only conditional operator in the following slides. So once we have familiar with different kind of operators, let's see what is its order of precedence. If you don't define any parenthesis, it will follow this order. If you define a parenthesis, the parenthesis will take the highest precedence. So the highest precedence of order is unary operators. After the unary operators, you will have multiply, divide and modulus operators, then add, subtract and shift. After that, you will have relation and equality operators, then reduction, then logical, and then the finally conditional operator. This we have seen, right? I mean, the conditional operator will be the least priority. Inside this, the expression will be executed first. If you have an expression like A into B, it will be executed first, and then the concatenation operator will be executed. Not concatenation, conditional operator will be executed. Okay. Now let's see the different examples by using data flow modeling. In this particular case, I am using a 4:1 multiplexer example as well as 4-bit full adder. Okay. Let's design a 4:1 multiplexer using data flow modeling. We have already seen how to design a 4:1 multiplexer using logic gates in gate layer modeling. Now let's do the same operation using data flow modeling. What is the 4:1 multiplexer circuit will look like? It has 4 inputs I0 to I3, and it has 2 control signals S0, S1, and it has one output Y. The output Y is connected to I0 if both are 0, 0, and it will be connected to I3 if both are 1, 1. Similarly, 0, 1 means it will connect to I1, 1, 0 means it will connect to I2. So in order to get this functionality, how to define this functionality using logic statements? Let's say my logic output, I have to assign my output. We know how to assign the outputs in case of data flow modeling, right? We have to use the keyword called assign. Assign out is equals to, I can define like this: I have S0 bar and S1 bar and S0 bar and I0, or I'm using OR here. This is an OR operator. And then S1 bar, S0 and I1, or S1 and S0 bar. This is bar, negation of S0 and I2, or S1 and S0 and I3. Simply you can write like this. What it is doing? It is doing AND operation of S0 bar and S1 bar, and then with I0 it is doing AND operation and giving a partial sum of, let's say this is P0. Similarly, this line is doing AND operation between these three inputs, I1, S0 and S1 bar, and this is doing an AND operation between these three inputs, I2. This is doing I2, S0 bar and S1, and this is doing I3, S0 and S1. We will have four different partial outputs, P0, P1, P2, P3. So P0, P1, P2 and P3, and then we are performing OR operation among all these four outputs. This is the output of a, this is my final output of a 4:1 multiplexer, right? It requires 4 AND gates and 1 OR gate. That is what I am performing here, and it is doing negation operation by using this negation symbol as well. In case of logic, in case of gate level modeling, we have to use gate level primitives like NOT gate, AND gate and OR gate to define the circuit, but here we are using a simple operators like negation operator, AND operator and OR operator to perform the 4:1 multiplexer. We will design this in the live coding session and we will apply different stimuli to it and we will check the functionality of this. This is one way of designing a 4:1 multiplexer using logic equations, and the other way is you can use a conditional operator as well to define the 4:1 multiplexer. So you can write like this: my assign out is equals to, I am checking whether the S1 is true or false, whether the S1 is 1 or 0. If my S1, so let me draw a 4:1 multiplexer table, truth table. This is my S1, this is my S0, 0, 0, 0, 1, 1, 0, 1, 1. My output will be I0, I1, I2, I3, right? This is the 4:1 multiplexer. So what I am checking is, if my S1 is 1, then again what I need to check whether the S0 is 0 or not. If my S0 is 0, then I have to assign my out. If my S0 is 0, then my output will be I2, and if my S0, this is question mark because condition I am checking. If my S0 is 1, so this is true statement, right? So the true value means S0 is 1, so it will be I3. This is false value. False means true means 1, false means 0. So if my S0 is 0, then I2 will execute. If my S0 is 1, I3 will execute. Again, this is when S1 is equals to 1. This is the true condition of S1, right? True of S1. What is false of S1? False of S1. So false of S1 I will define here. I am questioning whether the S1 is true or false. Once it is true, execute this step. Once it is false, now execute this step. In this step, again I need to question whether my S0 is true or false. If my S0 is true, then I need to assign I1, and if my S0 is false, then I need to assign I0. See, in a single line of code, you have defined a 4:1 multiplexer. That is the power of this conditional operator. What it is doing, it is checking whether the S0, S1 is true or false. If it is true, then execute this line of code, and if it is false, execute this line of code. Inside this, there is one more loop, one more if condition, whether the S0 is true or false. If it is true, then execute I1. If it is false, then execute I0. So with this, you have designed a 4:1 multiplexer by using a simple conditional operator. Now let's take one more example of 4-bit full adder. We have already seen how to draw a full adder using gates, right? The sum, let's say this is A, B, and C, and I have 3 inputs. So what does the full adder will look like? It will look like this. This is S1, C1. Using logic gates I'm drawing. This is, let's take C in. So this will come here. So this is my final sum, and the output of this will go to here. We need A into B to C in, right? A into B into C in, plus you will have, so you will get this is my carry out. So to define the full adder using gates, you will have 1, 2, 3, 4, 5 gates. But if I want to define by using a simple data flow operators, how to do that? I'm just defining using a concatenation operator as well. My C out comma sum, assign my C out comma sum, assign my C out comma sum is equals to A plus B plus C in. Simply by writing this, you will get both C out and sum output of the full adder. So that is how you can simplify your complete logic circuit into a data flow operators in data flow modeling. We'll have these examples once we do the live coding. We'll apply some different test vectors to it and we'll check whether it is working properly or not. So far, we have learned the theoretical concepts of data flow modeling, like what is an assign statement and how to use the assign statement and how to give the delay on assign statement. And we have seen different kind of expressions and different kind of operators that are available in Verilog. And we have seen how to design a multiplexer using the data flow modeling. In this session, I want to discuss all these theoretical concepts using some practical examples. So let's begin. So these are the contents of the session. First, I want to give you a clarity about these two operators, which look very similar, right? We have seen the logical, bitwise, and reduction operator. They all look similar. The logical operators will look like this, and the bitwise operator will look like this, and the reduction operator will look like this. They all look similar. So I want to give you a clarity about how to use them and when to use them by giving a practical example. And then I will introduce a concept called force constant and force clock, in which I will show you how to write the test bench without actually writing the stimuli or simulation source, and how to apply the inputs to your design without actually writing any Verilog code. We can do that by using a GUI mode also. So I will explain that in this session. And later, I will give you a very good example about regular assignment delay. We have seen that we can give assignment delays like this, right? Assign hash, whatever the amount of delay you want, you can give to the variable or net you want like this. So what does this do? It will do the output operation after 10 nanoseconds. So with this example, I will show you how the data is obtained by using the delay element in the assign statement. After that, I will design a 4:1 multiplexer using two different methods. One is by using logic equations and the other one by using the conditional operator that we have learned. And finally, I will conclude this session with 4-bit full adder with realistic delays. We will give delays to both sum and carry out by simply adding this statement in the assign statement. So let's begin the live coding session. So let me open the Vivado. Let's create a project. The first project will be the operators. I want to give you basic idea about logical reduction and this bitwise operators and how they are different. So let's create a file. I'm calling this as OP operators. Let's select our board, board. Next, finish. Now our project is created. I am assigning no inputs here. I will write the inputs in the code itself. So what will be my inputs? I am giving 2 inputs and I am taking 3 outputs to show the difference between 3 logical operators. What are the 3 3 operators? Not logical, 3 operators. First one is logical operator. Second one is your bitwise operator, and third one is reduction operator. Okay. So either you can write input and output here, or you can even write input and output in the module definition itself. So I will write like this: input, my A and B are inputs, and I can write output, my X, Y, Z are outputs. Okay. This is also correct. See, there is no error. It is showing green color. So it is correct. Now I am writing the assign statement. My X is equals to A and B. So this is a logical operation, right? I am doing double AND, which means I want A and B. If A is equals to true and B is equals to true, then my X should be true. If any one of them is false, then my X should be false. False means if A is equals to value 1, not equal to 0, or you can say if A is not equals to 0 and B is not equals to 0, then my X will be 1. Otherwise, else my X will be 0. Okay. And the second assign statement I am using for Y, I want my Y is equals to A and B. So what does this do? It will do bitwise and operation between A and A comma B. So it will do the bitwise operation between A and B, and then there is a okay assigned spelling is wrong. Next, I am assigning my Z equals to bitwise reduction operation. What does this do? It will reduce the vector, reduce my A vector to a scalar. Okay. It will do the bitwise operation of all the bits inside the vector and it will give the output. So this is a unary operator. You can see I am using only one operand and these two are binary because I am using two operands A and B. Now our code is finished. So we'll save this. And then after writing the code, the first thing you need to do is you have to check your schematic. So always follow these steps so that you will be consistently understanding what is happening in Verilog, right? First we'll create the schematic and verify the schematic is correct or not. Then we'll go for simulation. Then we'll do synthesis, implementation, bit file generation, and we'll dump our design on Z board or any of the FPGA board. So these are the steps I always follow. The first thing is we want to verify whether the schematic is true or not. What I did, I want my X to be A and B, which is a logical operation, and Y to be A and B, which is a bitwise operation, and Z is a reduction of A. See, both X and Y are using same gate, AND gate, but Z is using reduction AND gate. This is what we wanted, right? Why here they both are using same gate? Why not the other gates? Because since the inputs are 1-bit data, in case of 1-bit data, both logical operation as well as bitwise operation are same. That's why it is using same AND gate. Now let's simulate our code. Remember we didn't added any test bench, right? We haven't added any source of test bench, but still I am doing the simulation. You can do the same thing in gate level modeling as well as behavioral modeling also. Without test bench also, you can verify your source. See, in my sources I have only design source. Now the simulation source is created with the design source only. There is no top module which will define the inputs or stimuli that I need to apply. So what I am trying to do is I am trying to apply my inputs in the simulation window itself. So how to do that? There is a method called force. You can force the value of inputs in the runtime as well. So go to here, click right click, then you will get these options. Here there is option called force constant. Click on force constant. I want to give a binary since it is a 1-bit data. Let's take a is equals to 1 and force constant. My b is equals to, let's say, 0. Right? And then I am running the simulation of this force constant for, let's say, 10 nanoseconds. See, the a is equals to 1 and b is equal to 0 for 10 nanoseconds. That is what I have given here. And my x will be logical operation of a and b, right? Since a is equal to 1 and b is equal to 0, the logical end will be 0. Similarly, the bitwise end is also 0. 1 dot 0 is 0. And my z is reduction operation on a. Here only single bit is there. So as it is, the a is copied into z. So far this is correct, right? Now let's see by giving a vector of inputs. I want to give a vector of inputs 3 down to 0. Similarly, I want to get a vector of outputs 3 down to 0. Okay. Save this. There is no errors. Now again run. First of all, we will check the schematic. Right. It is asking elaborated design is out of date. Design source were modified. Yes, I modified the design source. So reload the schematic. Now see, it has created a very big circuit with different buffers and all. Right. Why it has created buffers? First of all, understand this circuit. The input, the output of this X is a logical output, right? Because we wanted output to be a single bit. After doing the logical operation, the output will be either 1 or 0. If A is true and B is true, then the output will be true, which is 1. If A or B is false, when I say false, here false means the data is 0. Comma, true means the data is 1. Okay. So that is why the LSB bit is the proper output and remaining 3 bits that it is connected to ground. It is connecting to 0, right? Similarly, the Z operator output is also a 1-bit data, but I have defined it as a 4-bit output. That's why it is only taking the LSB bit or actual bit data output at 0th location and remaining 3 bits it is assigning to ground. It is doing a 0 padding to the output. Okay. So the schematic is correct. Now you can see X and Y are divided because X is a single bit output that we wanted and Y is a bitwise operation which is a 4-bit output that is directly connected to the AND gate, and Z is a reduction AND gate which will give you a single bit output. Since we have defined Z as a 4-bit, it has assigned the MSB 3 bits to ground. Okay, the schematic is correct. Now let's run the simulation one more time. Now see, the inputs are in high impedance state and the outputs are in don't care condition, right? Now let's apply some input patterns. Let's say my A is a hexadecimal of 5 and my B is a hexadecimal of, say, E. Okay. Now I'm running for 10 nanoseconds. I want to see in binary, so I can right click here and change the radix of this to binary. It's also binary. Binary. Now let's verify whether the output is correct or not. So what we did, we applied 0 1 0 1 to A and 1 1 0 1 to B. So the first x will be the logical operation. Both the data are not equal to 0, so both are true. So true and will be 1. So x is correct. Now y will be bitwise operation between these two, x and y. So 1 into 0 will be 0, correct? 0 into 1 will be 0. 1 into 1 will be 1 and 0 into 0 will be 0. So y is also correct. And what is z is doing? Z is doing reduction operation on A. So it is doing 0 and 1 and 0 and 1. So any one of the input is 0, any one of the bit inside input is 0, then output will be 0. So Z is also correct, right? So let's apply some other different patterns. If you want to apply different patterns, you can use force clock. You can apply two different patterns in a single way. Like I want to have a leading edge of F and trailing edge of 5, and let's say I will apply for 50 percentage duty cycle for 10 nanoseconds. Let's see how the data will look like. I'm running the simulation for 10 nanoseconds. I haven't changed B, so B is as it is, but I have changed my A to two different values. This is my leading edge and this is my trailing edge. I have given F in leading edge and 5 in trailing edge, right? So we will check whether the output is true or not. In case of X, both the data are correct, so it is both the data are true, not equal to 0, so it is 1. In case of Y, it is doing bitwise operation between these two, and it is giving the bitwise output as A into B, right? A into B. First three MSBs are 1, so first three MSBs are 1, and this is 0, so this is 0. Similarly, my Z will be AND operation of these bits. In this case, it will be 1 because all are 1s, and in this case, there are zeros, so it will be 0. I can give my force clock with different duty cycle also, like this. Let's take my leading edge as 7 and my trailing edge as 0, and I want to give a duty cycle of 20%. What does this mean is, this leading value will be 22 nanoseconds. 20% of 10 nanoseconds is 2 nanoseconds, and trailing edge will be remaining 8 nanoseconds. So we'll see, we'll run the simulation. Let's say I want to run the same input pattern for 2 times, so I'm running it for 20 nanoseconds instead of 10 nanoseconds. So the same input pattern will be appear for 2 times, right? See, this is the first time it has appeared, and this is the second time it has appeared. You can see the duty cycle here. It is only 22 nanoseconds. It started at 1020 and it went up to 1022, and the remaining 8 nanoseconds is the trailing edge value. Okay, and the outputs are also as it is, whatever we explained. If my all the inputs are ones, then only the Z will be 1, otherwise it is 0. That is what happening here. And here X will be logical operation of A and B. I want X to be 0, so how to get X to be 0? Both the inputs should be zeros, right? So let me change the value of B to 0. I want to change, just simply I'm changing the constant to 0 instead of clock, and we will run it for 20 nanoseconds. Now X should become 0, right? I mean, I want it to be 1, so both of them should be 1. So let's take constant of F as well as B also, F. Okay, now let's run this. Now see, my Y is equals to 1 both if both my inputs are 1s, right? My X will also be 1 because this is a logical one. If both are true, then it is 1, and my Y is bitwise operation of these two, all are 1s. And similarly, my Z is AND operation, reduction operation on A, so it is 1. our output is correct. So this is an example to demonstrate the difference between three operators such as logical operator, bitwise operator, and reduction operator. I hope this is very clear to you.